Okay, good morning again. I see that some people have handed in the few homeworks that we've had. Please make sure you are turning those in to the Google Classroom. Today we're going to go over the homework. We're going to learn about ionic solids, and then we're going to learn about Lewis dot formulas. We did those earlier in the year. And then I'm going to give you show you how to do the homework that will be due for tomorrow by noon. You should have the sheet. Okay? So let's look at the homework first. I did put corrections on those people who had them. So all you have to do is really look into your notes for this. Chemical bond is an attraction between one atom's protons and another atom's electrons. You could switch those back and forth, electrons and protons. It's the same thing. You could have also put one atom's nucleus, because what's in the nucleus? Oh, the protons are. So you could add either one of those. Remember, they are attracted because opposite charges attract. Electrons are negative, protons are positive, they'll attract that way. Okay, sorry. Atoms always want to be at their most stable and have the lowest amount of energy. That's why they make bonds. If they're very stable, they're most comfortable, quote unquote, and if they have the lowest energy, that means that they're also most stable. Ionization energy, just from your notes, is the amount of energy it takes to pull an electron off of an atom, and that depends on a number of different things, and all of those are in your notes. Electronegativity is the attraction of one atom for another atom's electrons. So if you and I are sharing electrons, if I have more electronegativity, I can pull on the electron, your electron, and maybe even pull it all the way off. There are different degrees of sharing though, and we already looked at that from the homework. If the difference between the electronegativities is high, say greater than or equal to 1.7, then essentially I'm going to hog the electron to the point where we call it an ionic bond. If the the difference between electronegativities is less than 1.7 but greater than 0.4, we call that a polar covalent bond. We'll look at covalent bonds tomorrow. Covalent bonds is more of like a sharing between the electrons, of the electrons between the atoms. And if it's less than that, we call it just a non-polar covalent bond. But we'll go into more detail with that. So electronegativity is the amount of attraction an atom has for another atom's electrons. And then the trends. Now remember that ionization energy and electronegativity go hand in hand. If one goes up, the other one goes up, and if one goes down, the other one goes down. So let's take a look at our periodic table here. You might remember that if we go across a period, these are periods 1, 2, 3, 4, 5. If we go across a period, there are more protons. Beryllium has one more proton than lithium. And since we're not adding another energy level, remember these are the energy levels that we've been talking about. Here's the nucleus, and here's the first energy, second energy, and third energy level. That's where the electrons are. Since we're going from left to right, we're adding protons. You can tell that by the atomic number, 3, 4, 5, 6, etc. But we're not adding a energy level. We're staying at the same energy level here, and because of that, the atom is going to have more protons and pull on the electrons even more. So as we go from left to right, the number of protons goes up, but the atom actually gets smaller because it is pulling on those electrons even more. So fluorine has the highest electronegativity. It really wants electrons from other atoms. It also has the highest ionization energy. That means since those electrons are closer to the nucleus, it's harder to pull them off of fluorine compared to almost anything else. The exception here is the noble gases. Those are very stable and very hard to pull off. So from left to right, ionization energy and electronegativities go up. If we go down a group, remember these are groups 1, 2, 3 through 12, and then 13 through 18. These are groups, and they're groups because they have a number of electrons, same number of valence electrons, or outside electrons. As you go from beryllium to magnesium, calcium, strontium, etc., what's happening here is we have the same number of valence electrons, but we're adding a PEL, an energy level, each time. So we're adding one of these every time. And because of that, these electrons are getting further and further away from the nucleus. Because they're further away from the nucleus, it's going to be easier to pull an electron off as you go down to barium and radium. Because of that, ionization energy goes down. Now, what would the attraction be between barium and strontium? Well, this one is a bigger atom, and because of that, there are more electrons in the way. We call that electron shielding. And because there are more electrons in the way of the attraction from the protons, then the electrons are held less tightly by the proton. So it's going to be easier to pull an electron off of barium than it is to strontium, because strontium's electrons are closer to the nucleus. There's a greater attraction. So the general trend is, as we go down a group, ionization energy is less because it's easier to pull electrons off. And electronegativity is also down because with all of these electrons in the way, that minimizes the amount of attraction that an atom with multiple, like strontium has less pull on electrons than calcium because there are other electrons in the way. Okay, so those are the trends there. All right, let's look at the notes for ionic solids. Again, you have these all filled in. Substances in the solid phase that are formed by ionic bonding. And at this point, you should be able to look up at the periodic table and find and make up some ionic compounds. Remember, from here over to the stairs, these are all metals. From here to here, they're called transition metals. These are a little bit more predictable. And then on the right side, those are all nonmetals. So if you pick a metal and pair it up with a non-metal, it's going to be ionically bonded, and oftentimes it will be an ionic solid. Okay, so sodium chloride, magnesium oxide, and calcium chloride. All those are examples of ionic solids. There are characteristics that you have to know too. They have very high melting points, sometimes in the thousands of degrees Fahrenheit. They do not conduct electricity. Just as a solid, it will not. However, unless we say it is molten, and molten, think of molten lava, molten is a solid that you've heated up to the point where it's actually liquidy, but it's still just that compound. We can also do the same thing if we have them in water, because ionic substances, when they're put in water, they will separate into their ions. I'll show you that here in a second. We say that they are crystalline in structure. In other words, they make crystals. And you can see that by the structure here. They're very rigid, And you're always going to have an alternating pattern of positive ions and negative ions. That's what makes up the solid. And they're also very hard. Let me see if I can swing this around to show you a quick demonstration I've got set up. So this is an electronegativity, a conductivity apparatus. So if I take these electrodes, I've basically got this plugged into the wall, and I let these wires touch, it'll allow the electrons to go through here and light the light up. Now if I take an ionic solid like salt, I've just got a pile of salt here, and I stick it in there, it's not going to do anything. The electrons can't flow in there. However, if I stick the electrodes in a solution of this, I'm not touching the wires in there, it's just in liquid, which is water, it will allow the electrons to flow. Okay? That's the demonstration. Here's distilled water. Distilled water has no ions in it at all. That's why the light doesn't light. This is tap water. Tap water that you just get right out of the tap, out of your faucet. Tap water does have some ions, and that's why you end up seeing the light. Electrons can flow in that case. Okay? Just wanted to show you that very quickly. Let's look at got about 3 minutes to show you Lewis dot structures. We've already done them. So let's look. Still. Okay, Lewis dot structures. Remember Bohr models? We just did some up there. It's also known as, the Bohr model is also known as the planetary, where we say that the electrons are in orbits. And later on, probably, we'll learn about electron clouds. And those are called orbitals. Now, there are electrons that go on the outside, and those are, we know that already. Those are called valence electrons. And they have electrons inside of them. Anything inside are called the kernel electrons. Okay? So what scientists have done is to put together a system here called Lewis dot formulas. Remember that the first two electrons are placed above the symbol, and the rest are put in order in clockwise fashion. I'm probably going to run out of time. Let's look. I've got about a minute. So I'll show you this first one. Here's the homework. On this homework, I want you to do carbon, helium, and fluorine. We'll do calcium together. Calcium is 40-20. That means it has, we're going to skip the Bohr diagram actually. It's in group 2. That means it has 2 valence electrons. And I've got calcium here. If it has 2 valence electrons, I just put 2 electrons there. Then I'm done. Okay? That's basically it. It's pretty straightforward. Okay? So, actually, why don't you do sodium as well? It's not going to take you very much time at all. And then I will put that as an assignment on the Google Classroom. See you tomorrow.